So we're all welcome to the class for the day. And I've stated in the topic, we're looking into the role of hyperparameter tuning in ML-based, machine learning-based modeling. So when we look at in the previous week, we actually look into the idea of implementing your first ML-based model. So, and also which we termed Hello World. So welcoming practice to the ML system modeling. We discussed several cases here whereby this is. So we look into how we can actually start from the scratch. So look for your data sets, try to model it, look for the appropriate features. In the first three videos on this series, we actually demonstrated how we can do that, including we look into diabetes case and also look at another case of using interview-based data set. Sometimes you have problem getting the data from the clinic. You can also, in collaboration with medical doctor or people in the know, you can get data by actually using simple questionnaire-based data collection. Because the most important thing is that without data set, you cannot really achieve anything. So we also move into, we also look into the customer shown as a case study in telecom company. And we actually call our attention to a situation whereby the provided data set might be lacking in some very important factors. So you as the developer or as the professional, you have to look into the data and offer appropriate help. From here, we can see, we notice something is missing. So we say, okay, age is very important. At age, we go a long way in determining if a customer will stay or not. Young generation of people are not likely to stay longer in a particular telecom company. So they keep switching from one place to the other, depending on the advantages as it comes, where an elderly person might not have time for such exploration. The gender also could play a role, which was conspicuously missing in the first data set. So getting appropriate data set actually might enhance what we want to achieve. So we look into some of these and then how this is connected finally to the summarized steps. On getting started with your ML modeling, we discussed this extensively in our three previous videos, where we ended it by saying, by providing this summary, identify your area of interest, look for free online data set to start with. Don't wait until you get your data set that you want to use. Get a free data online. There are so many data sets online. We provided link to several of them in our platforms. So then try to build your first ML model, do the hyperparameter optimization, this is going to be the point of consideration majorly today. So what is this hyperparameter optimization and why is it important? Is this something we can ignore? So we're going to look into that today. After that, you analyze and discuss your results, document your experimental outcome and findings, disseminate your results. So based on the experience from the online data set, you try to gather the new data set related to your area of interest. So I said, contact interested parties, give them the kind of assurance that you are going to treat the data set with all respect and the confidentiality that they demand. Sometimes they might even ask you that you don't mention their name when you are going to publish your work. So, of course, their name is not important in your publication, in your work. So you have to agree to whatever condition they put into place to facilitate getting the data. Otherwise, also considering interview or questionnaire-based data collection is another option. People are getting into this option these days, and they are getting data set that even some of the little, very simple questions we talk may not make much difference in those areas for modeling and predictive analytics. They are coming out to be very powerful, actually. So this is an area is being practicalized now, it's being demonstrated, and encourage people, especially when you have made a lot of effort and seems getting data from the targeted source is not working. You shouldn't lose hope. So there's always a way out of every situation. Perhaps you may need to explore the option of interview or questionnaire-based data gathering. Then you have to do the new modeling using the new data set, again, analyze, document, and then disseminate your work. Because even while using the initial data free online data set, you've seen people sometimes get confused. They think that online free data set, can we publish with it? Yes, if you're a researcher, you can actually publish your work based on online data set. Sometimes you might be the first one. Some people actually uploaded data set that has never been used in any research. That's a good start for you. And if someone has done it before, you have used this data set, then look what, is there any way you can actually improve upon what they have gotten? Especially very, very important data sets. You see some of them, they're just having maybe 60% accuracy, 70%, or sometimes you might look in the direction of the misclassification error. The mistake they are making is on the costly side. For example, in medical, if somebody is having medical prediction and the mistakes, all the mistakes are coming from false negative. False negative means that someone is sick, but the system is predicting the person has not been sick. This is a mistake that is not acceptable. Of course, every mistake is unacceptable, but one is more serious and dangerous than the other. So when you find out that the mistakes are coming from the costlier side, then that means they're still even if they have achieved a very high accuracy, in that case, you still need to do a lot of work to reverse that trend, to either make sure that there's no mistake from any side, or at least you try to push the mistake to the less costlier side. That is, having mistake from the side of false positive. False positive means that someone is not sick, but the system is predicting that person has been sick. He'll go for further checkup and he'll be exonerated and discharged. That, oh, we are sorry, this is ML mistake. This is better than having someone discharged that is not sick, meanwhile is sick, and then it will degenerate to complicated situation. So this is just a kind of clarification on that even while using the free online data set, you can still do very interesting work to actually improve what has been done before, and then you can communicate the research community about what you have done. So today, like I said, we're going to look into the role of hyperparameter tuning after you have successfully got the data set, either free online or your new sample data set. Now, it's not just enough. Based on our interaction in the past few weeks, you notice a lot of people are still making this mistake. They just get the data set, run the modeling, and because they are getting 98% in one of the algorithm. Let's say somebody decided to use KNN and also SVM. He achieved KNN with 98% accuracy, and then maybe SVM is getting 95% accuracy. He declared, oh, wow, this is wonderful. Then he started to write, it's done, it's the first one, it's a new data set, and he think I think this is excellent. It can go. This one can go later, it can do some improvement later and the like. Yes, 98% is very excellent work. However, something is missing. There was nothing about hyperparameter optimization. See, doing hyperparameter optimization is not optional. It is compulsory. You see, mostly people work with default parameters. That is, when you open a machine learning algorithm in any platform, there's some default parameter. For example, k nearest neighbor, the default parameter for value of k is always 1. K is usually equal to 1. You see, for support vector machine also, you have their own default. RBF is often used as the default parameter for the kernel, RBF. So people use this as default, and then they run the experiment and they conclude, and then they start writing and they say, I'm ready to submit. See, practically recently, one student did that and got rejection from the targeted paper. The major comment was about missing hyperparameter. See, when you miss hyperparameter value, the fact that you are getting excellent result, even if this k-nearest neighbor has achieved 99% accuracy and you think this is excellent, even 100%. You see, but however, you are comparing your work with this guy. You are saying that support vector machine is getting 95%. This one is getting 100% or 99 or 98. by using default parameter. So by coincidence, maybe it happens that the k equal to 1 default value for KNN was better for your data. You know, we always say, let the data speak. Let the data speak. Let the data speak. Very important policy. Now, so while doing that, you are declaring that SVM is not fit for that data. So in essence, you are not being fair to this algorithm, because you might be surprised that by the time you change this default value from RBF, the Gaussian hyperparameter value, when you change it to polynomial in support vector machine, maybe support vector machine will get 100%. But however, you are misrepresenting SVM as not being okay for this data set. So that is why when you refuse to do hyperparameter optimization, you are not just missing possibility of getting better result using another algorithm. You are also lying against that algorithm. You are saying that this one is not good. Meanwhile, you didn't do the right thing. So it's something that is very, it's compulsory. In fact, your work can be rejected based on this, because you are not being fair. Every algorithm needs to be given the fair hearing. And being fair is that you have to check for all the hyperparameter of every algorithm to see that, yeah, can they really model this data? Because the best of them, sometimes there's no really a machine learning algorithm that is best in all situations. So you have to check based on the principle of let the data speak. Now, as the procedure goes, we all know this is a generalized pattern of our modeling scheme. You have the data, you have the algorithm, and modeling. This is modeling. You check the performance, and then you can go back. Here, you can do the hyperparameter here, hyperparameter tuning. So you keep tuning the hyperparameter. And sometimes you might also need to change the algorithm from KNN to SVM, from SVM to decision tree. So you can keep going here. However, because you might have to go back to do feature engineering or feature selection, as the case may be. But feature selection is totally optional. Yeah. However, why feature selection could be optional, especially if you are getting excellent result with all the features, you don't have time, you already got what you need 100% or 99 or whatever. Feature selection has its own advantages. We can talk about that later on. We already discussed also before. However, for parameter optimization, hyperparameter tuning is not optional. We just have to do it. Not doing it and reporting it is a big weakness of your work, and it is not acceptable. So we have to take note of this. So in recent time, I've seen a lot of people making this very big mistake. They have done 15 experiments, oversampling, undersampling. A lot of all these are actually optional. So, but parameter optimization or hyperparameter tuning is not optional. So, and to know that hyperparameter is different from parameter. Parameter is generally whatever value we send to a function. See, you have KNN, then function, you send a K to it. You also send in the distance measure, maybe Manhattan distance measure, and also the number of decimal places. So number of decimal places is a parameter. However, K and distance measure is hyperparameter. The definition of hyperparameter is that these are the parameters that will affect the performance of the algorithm. You see? So other parameters like number of decimal places, it doesn't matter either 2 decimal places, 5 decimal places. It doesn't have effect on the performance of the algorithm. However, number of K and the distance measure you are going to use seriously affect the performance. Therefore, hyperparameter tuning are very, very important in machine learning-based modeling. So it allows the data scientists to tweak model performance for optimal results. So you want to get optimal result, you can change this hyperparameter. You don't go with default value. Sometimes default value might get you the best result, but you still need to check out, perhaps maybe other values will get better result than this default value. And if you use default value for one and you got better result, the second algorithm might not work better for default value. So you have to be fair to them. This is raise a kind of an integrity question. So when you just use default value for all the algorithms, and then you report the algorithm with the best result based on default parameters, this is not valid. This is not correct. So you have to subject each and every hyperparameter, every model to hyperparameter tuning. We said the process is an essential part of machine learning modeling process, and then choosing appropriate hyperparameter value is crucial for success and for the acceptability of your experiment. Because it's not just for you, what experiment you are doing is not for you, it's for the larger community later that you're going to publish your work, people are going to check it out. So you must do and follow the expected or the laid down procedures. So how do we do hyperparameter tuning? It can be manual or it can be automated. Automated means you can automate it, you can use some optimization algorithms, you can do grid search. These are the popular one often done is the grid search method. The grid search, here you have to be done by writing a kind of several nested looping system, whereby you're going to be picking the parameter, then change it randomly. So you have it here. So you set the value for this. As you are changing this value, you also change another value. So we got the grid search. However, the often recommended, especially for beginner, is manual, or we call the random search, or what I call systematic manual search. So while manual tuning is slow, it could be slow and tedious. However, a benefit is that you understand better how the hyperparameter weighting or effects or how they affect the model. So you can feel for yourself how the model performance is changing as you are changing the hyperparameter values. So it's a good learning experience for you rather than just clicking a particular automated system that will run it, in which case you might not really know what has actually transpired. So ahead of the method, I personally used to recommend for my upcoming student that, okay, please use manual or what I call systematic search. Try to identify some of the very important hyperparameters of your algorithm and then take them one by one and search for the values that gives you the best result, and then move to the next one. And then you do this until you can never make it better anymore, in which case it can guarantee for you that you are going to get better result. And you have to do it for every algorithm you have chosen to use. So say the process of hyperparameter tuning is iterative, and you have to try out different combination of hyperparameters and the values. Yeah. And generally you start by defining a target variable such as accuracy. So you have to identify what am I going to use to determine when to stop, when not to stop, when the value is okay. You can choose accuracy and root mean square error for classification and regression respectively. Maybe I'm dealing with classification. The accuracy could be what I'm going to be checking. So I'll be checking the accuracy value as it moves up. So while for regression, I might be checking the root mean square error. Sometimes it could be maximized or minimized. See, for root mean square error, I want to minimize it because the smaller, the better. Whereas for accuracy, the higher, the better. So that's why hyperparameter optimization could be maximization or minimization problem. See, depending on the performance measure that you want to use in checking when to stop after getting the best possible outcome. So, and another thing to note is it is always a good idea to use cross-validation techniques so that your model is not centered on a single portion of your data set. This is very important. See, often than not, people often use 80%, 20% for hyperparameter optimization. The disadvantage is that, see, you have fixed this 80% as the training set, and then this 20% as the testing set. It means that your algorithm is going to be using the same training set throughout. So the training idea, the hyperparameter is not adjusted to several possibilities. So that's why the best practice is for you to, first of all, divide your data into two. Let's say 70%, then 30%. Keep this 30% out of it. Use this 70% for the hyperparameter optimization. You see, you don't use their testing set. You don't use the hyperparameter optimization. You keep it totally out of your file. You bring it in later on. See? So this 70%, then you can use cross-validation idea, in which case you are going to split, the system will split it into this 70%, maybe 70% could be like 700. Let's say we have 700 samples. So let's say we want to use 10-fold cross-validation. It will be divided into 10 places. That will be 70, 70, 70 in 10 places. So the idea of cross-validation is it will pick the first 70, the first 970 partition. That is 1, 2, 3, 4, 5. Let me make it easier here. I have 70 here, 70, 70, 70, 70, 70 in 9 places. So it will pick 1, 2, 3, 4, 5, 6, 7, 8, 9. It will pick this 70 in 9 places, add all of them together, merge them together, and use them for training. And then use the last 70, which is the 10th one, the 10th portion, use it for testing. And then you record the result. Maybe the result is 92%. Then you have to keep using that. It will do that for 10 places. Then it will use this one, bring this one back as part of the training, and then add this to it, add this to it, add this to it, and then take this guy for testing. So it will be doing that up to 10 places until this one is used for testing, and then to get the result. So in essence, we're going to have like 10 results. Then it will find the average based on that. So your decision of what is the hyperparameter achievement, for every value of hyperparameter, it will be taking the decision by using the cross-validation. So this is the recommended practice that, though it's not compulsory, but this is better to use the cross-validation techniques so that your model is not centered on a single portion of your data set. Now, so I would like to demonstrate maybe at least one or two examples. Let's go to our weaker environment to see either for classification problem or, let's say this is class. Let's really for today, let's look at regression problem. So as usual, you bring in your data set. So I mean, weaker environment, I hope everybody can see the weaker. So if you're not seeing it, you can type in the chat to let us know that you are not seeing it. So these are the attributes. This is the targets. It's what we want to predict. We want to predict permeability in oil and gas. So it's a regression problem. You can see here, it has the minimum value and the maximum value. So we have the correlation. These are the attributes. The depth usually is often not used for the prediction, so we can remove the depth. This is the depth of the measurements. So often we don't use it for prediction, we can remove it. You can bring it back later if you need it for anything. So we remove it now, we are left with 11 attributes, and then the last one being the targets. So we go to our classifier. So the idea here is that we want to do hyperparameter optimization. So what is good is bring in the 70% of your data set into the CSV file before you upload it to system. So the remaining 30%, you have extracted it and put somewhere else. Or it could be 20%. It's up to you. Now, let's assume we have the 70% now in the Excel file. So it's already loaded for us. So we go to classifier. So we have to set how do we want to partition the data. We can use this. We want to use 80, 20, whatever. However, for hyperparameter optimization stage, it's always good for you to use cross-validation. So for the sake of time, you can use 5-fold because 10 will mean we're going to be running it 10 times. So to save time, you can use 5-fold. So if your data set is not much, it's even highly recommended that you reduce the number of folds. However, if you have big data, that's good. The fold can even increase to 20. It's up to you. However, 10-fold is very, very common because of the uniqueness of 10. When you divide anything by 10, it's very easy to distribute them accordingly. So now let's check. We're going to use, as usual, our friend, the k-nearest neighbor, as an example. So when we choose the cross-validation approach, see, it's running. So here, this is default value. I just run the experiment now. This is my mean absolute error. The correlation coefficient is very high. The mean absolute error is 9.57. So I go here if I want to check the hyperparameter values. I want to change the hyperparameter values now. I want to do tuning of the hyperparameter. So you have to click here. See here, this is default value. K is 1. See? And inside here, you have the Euclidean distance as the default. So these two hyperparameters, you need to tune them accordingly. So in this sense, we go here, we start to change it from K. You pick it one by one in the systematic, simple one. So once we identify the most important hyperparameters, take them one by one and then try to tune them. And how do you know the most important ones? It will be listed here. If you are using weaker environment, it will be listed here. You can see K is listed as 1. And the second one is the Euclidean distance. These are the two hyperparameters that are important here. You see, even though you can see this is parameter, batch size, debug, distance weighting, mean squared, number of decimal places, these are all parameters. Hyperparameter is also a parameter, but hyperparameter is a parameter. Not all parameters are hyperparameter. So hyperparameter are those that are uniquely attached to the algorithm performance themselves. Therefore, they are KNN. So you have to change. We want to start with K. Now K is equal to 3, for example. So we want to see what we're going to get. Maybe the result will get better or get worse. So we have to run it. So you can see that this is why if you look at A, see, this is the initial one. That's why I recommended root mean square error. Root mean square error. To me, it's a very good determinant of the performance of regression problem. So you can see root mean square error. You can easily notice the improvement in root mean square error, unlike the correlation coefficient. You can see this is 23.13. That's the error, root mean square error. In the second one now, after changing it, see, we see how it is performing. Is it improving or is it increasing? We have to check. So we use again. Let's say we want to use 5. This case may be, we run it again. We can see that since the performance is going down, because root mean square was 23 before, now it is 28. It means the improvement is really, the performance is getting worse. So we have to quickly go back and say that, okay, perhaps maybe 1 is the one that is giving us the best. Like I said, sometimes default value could give you the best depending on the data set you are using. But then we are not done yet. You have to go inside the Euclidean distance. For example, the distance function. Euclidean distance is the default. Now it's time for you to change it. Maybe you want to change it to Manhattan distance, Mayor, and then you run it. Run it again. And take note of the result. You can see the result is 22.16. You see, it has gone down. And I said this is minimization because this is error. The lower the error, the better. It means Manhattan distance is solving this problem better than Euclidean. So we got to fix that one because 1 gave us the best. Then we keep changing the distance. Again, we want to check for another one. maybe Minkowski distance measure, we get better result for us. We see it goes up. You see, the root mean square error has gone from 22 to 23. It means it's worse than the previous one. So we keep changing this until we actually get the 1, 2, 3, 4, 5. There are 5 options here. Once you try all the 5 options, then you go with the one that achieves the best. Then you can now conclude that for my k-nearest neighbor modeling for this permeability problem, the best result for me is gotten when my distance measure is set to Manhattan distance, and also my k is set to 1. So we are done with that. That is that algorithm, you are done with it. And you have to report those values in your writing, because somebody can pick your work and reproduce what you have done, having gotten access to your data set. And you have to let them know that for this hyperparameter, I use 70% of my data. And I also use the cross validation method to break my data. All what you have assumed or procedure you have taken must be reported. Anything that if you don't say it in your experimental description, people will not be able to repeat your experiment. You have to make it very clear. This is very, very important, because sometimes people just assume this and they will not put in their report. People will not be able to reproduce your work. If they cannot reproduce your work, it means your work is not valid. So you have to tell them, I use cross validation, I use 5-fold. You have to tell them it is 5-fold. Because somebody will use it and want to use 10-fold. It will not get the same result. So you have to make sure you mention whatever you have assumed during your experimental procedure. This is very, very important. So let's say, for example, again, on this same problem, I want to try SMO-reg, which is the support vector machine for the regression problem. Which support vector machine for the regression problem. Yeah, so we have to follow the same procedure, but however, it's very important that we understand. The first thing is to know what are the very important hyperparameter values that are important for support vector machine. You see, when you go here and you put your stuff there, over it will tell you this is SMO-reg, this is implementing the support vector machine for regression. You want to know what does it mean? It is implementing support vector machine for regression. So this is very important. You have to know what you are implementing. For support vector machine is one of the very, very powerful and very interesting and unique machine learning algorithm. So, however, for the sake of our time today, we might not be able to continue with support vector machine, but I want us to deal with support vector machine, possibly by our next sitting, hopefully. So we'll be able to pick it one by one. But note that today, we dealt with k-nearest neighbor, and you get it from here. We call it the lazy classifiers. So from the group of lazy classifier, the IBK. Again, also, you have to, if you over it, to show you what it's doing. This is k-nearest neighbor. Yeah, we started with k. Your k can go from 1 to as many as possible. So when we started, we go from 1 to 3, then to 5. Then it started degenerating. We moved back to the best one, which was 1. Then we also went into try to work for the distance measure, where we check it, Chebyshev. We also check for Euclidean, we check for the filter one, Manhattan. Then you have to select the one that's going to work for the best among them. So having done this, then that classifies that for the k of k-nearest neighbor, you have been able to do what we call the hyperparameter tuning as it should be. And you have to report whatever assumption that you have actually made in the course of this. So this is because of our time and some other commitments, so we're going to actually call it a day today to give little time for, in case of any clarification or question to ask regarding what we have discussed today. So by the grace of Almighty God, by next week, we are going to continue from where we stop. So looking at how we can do for the other one or two examples and some other clarifying points that is very important when we do hyperparameter optimization. So taking us back, so the role of hyperparameter tuning in ML-based modeling, so how we can do it, why we need to do it, and some of the mistakes we should avoid making. Thank you very much for listening. I think we are going to now move to the question time.